As you may be aware, a diversity of computational methods have been used to generate sounds on computers. The foundations of working with audio are using frequency as a power of 2. The 12-tone equal temperament scale is derived as seen here. You may want to use a just intonation if you're not switching scale a lot, which means selecting your favorite ratios. Dynamics work exponentially, which is why an exponential contour is used for amplitude because it has a constant ratio of change, for example, exponential decay. By changing the gain coefficient we change the rate of amplitude decay. To calculate a coefficient for a specific length of decay. To calculate a specific amplitude after a set number of iterations, we use the inverse. Given any two of these variables we can derive the third using the identities. To produce an exponential envelope attack contour where the signal rises from 0 to a desired amplitude, say 1, the simplest method to me is to use linear interpolation. So, we have a simple attack/decay, two-stage envelope. The first signal we can generate to envelope and amplify is noise. Game developers have significantly misinformed ideas about random value generation. Here is a non-repeating, statistically balanced method of generating random values. It's from Hal Chamberlain's 1980s classic on computer audio. In digital audio we are limited to half the sampling rate as the shortest wavelength we can produce without aliasing, which reflects any higher frequencies back into the audible range inharmonically. We want to avoid that. Reducing aliasing frequencies in a generated signal is the region of intense focus in audio DSP, digital signal processing. We can add a low-pass filter using a buffer variable and the same process as linear interpolation. By smoothing between the buffer and input, a 6 dB/octave low-pass effect is produced. We can get a 6 dB/octave high-pass response by subtraction. The 6 dB/octave rejection cutoff frequency is at -3 dB in the response curve. The cutoff frequency in this filter can be specified using angular frequency, denoted with a lowercase w. Angular frequency is very useful. It's also the square root of k, the spring coefficient. In game audio we often want to send parameters from video frame rate processes to audio rate processes, for example, a distance for a delay effect. I use a low-pass filter structure in the audio process to pass variables to audio processes, so no stepping is hard. Try starting around 0.001 for smoothing rate and adjust until the effect sounds smooth without lagging. There are too many useful things to be aware of about audio to fit into this video, but one general piece of advice is put a high pass on the main outs. High passes remove biases in the waveform and pull it back to the center line, reducing peaks and grinding the signal into the rails. The quadrature oscillator is a form that uses two states or variables, S0 and S1. If we initialize S0 at 1 and S1 at 0, or at any sine and cosine pair and run the form, S1 and S0 yield sine and cosine waveforms in quadrature at angular frequency. S0 is half a sample behind. This form eventually explodes due to numerical error and can be renormalized every buffer if it needs to run continuously. More often I use this form as a bandpass filter. It's a cruddy sounding filter with about 30 decibels rejection, so it works better as a resonance. Using a small number of resonances can effectively emulate natural sounds for game engines. In-game, it will be difficult to discern between a sample of a breathy sigh and filtered noise with a couple of resonant foment bands. Gravel footsteps and other rough sounds can be emulated by using a few resonators triggered by a noise impulse which has been thinned by logic gating. You are also looking at the classic drum machine circuit here. Perry Cook's STK is a rich source of minimalist synthesis architectures. My sound effect engine has a set number of voices, for example, 32, which are paged through as new events happen. The same architecture can handle several classes of sounds. Placing sounds in the environment with distance and panning helps. I've always used cosine panning law. I think SPL laws use the same distance squared attenuation as light, but I use 1 divided by 1 plus distance asterisk scalar in games since the world is simplified. Delay lines are the building blocks of reverb, spatial and acoustic modeling and key effects. Declare an array and length for the delay and one pointer for all the delays. Quality is perfect if you use INT-length delays that aren't modulated, but linear interpolation is smooth enough to modulate delay length with only minor loss of high frequencies. Use second order or better interpolation if you are simulating piano strings. Floats are fine for most audio applications, save the overhead if you can. 44100 is fast enough to use delays to model acoustic spaces to a fine enough degree for voice synthesis, for example. The Kelly-Lochbaum tract, which uses waveguides, or pairs of delays running in each direction to model transmission. If you are modeling an acoustic space, some general guidelines are use cosine law for reflection amplitude. If I remember correctly, an acoustic surface reflects frequencies above a quarter wavelength of its flat or open dimension, i.e. small panels reflect bass frequencies poorly. For general consideration, sound propagates directionally above human hearing instead of radially, which is convenient for ultrasound. One of the primary components everyone neglects is ground plane reflection. It's significant enough to impart a perceptual tone to jet engines. Next time a plane flies overhead, duck your head towards the ground and you will get a big surprise, so that at 2.5D, audio engine which does model ground plane might be the second of its kind, winky face and add an interesting experience of motion. Would anyone recognize it? Reverb topologies attempt to maximize dispersion using DSP abstraction. An essential element for spatial modeling is the all-pass filter, which passes all frequencies without attenuation but with phase delay, producing dispersion akin to acoustic transmission in solids. A delay line with a high gain all-pass does the Star Wars laser wire thing. All-pass filtering stops a delay network from sound like a bunch of taps and turns it into cream. In my most recent project, I used a simple moving reverb abstraction which is not strictly accurate but close enough to be effective. 4 Cartesian points are extended from the camera position to the walls. 4 delay lines model the delay from these points to the listener. Each sound-making object in the room has one delay line associated with it, with lengths/distances to each of the 4 points and to the listener. Even though modeling only a single point on each wall is a gross simplification and the distances are slightly inaccurate using this arrangement, the primary modes of the space are modeled with locational sensibility. All-pass filtering adds enough dispersion to sound like parallel surfaces. Oscillators. A naive sawtooth waveform constructed like this would alias too badly to use for music. One simple workaround is just to treat the samples around the transition point, which can reduce aliasing by 18 decibels. Handling the transition point like this allows you to create a waveform with almost any shape you want between phase 0 and 1. I believe this is the second order form, but I haven't tested it myself yet. The anti-aliasing should be around 36 decibels. If you can have faith or make sense out of my documentation of Mistran's BLEP OSC code, it's a wonderfully anti-aliased oscillator that fades between saw and pulse width adjustment. Voices and soft musical sounds can be made using naive/analyzed oscillators with softer harmonics to combine with resonances. Harmonics of the oscillator still extend for several kilohertz, creating a reasonably lifelike sound. Here's an example for phase running from 0 to 1. Temp is 0 at both ends, and 0.25 in the middle. Next. Temp is now an almost sine contour from 0 to 1 in amplitude. Squaring it again produces a soft tone with a few harmonics that won't perceptibly alias in the musical range. Doing everything the canonical way avoids obvious optimizations. For instance, the decay contour of snares and other percussion instruments is often linear instead of exponential. So sometimes cheap and cheerful works out. My guess is that most people have no objection to using a few transcendentals per oscillator per voice and will reference and implement canonical frequency modulation or phase modulation algorithms, so hopefully the curious notes in this oscillator section haven't been too debilitating. Filters. This section is less dubious. Here are a few references and forms for the canonical filter types. It's worth knowing that there are more intensive methods if filtering, such as sync and Fourier methods. Guide.com is a classic and clear read. In the early 2000s, a second order, 12 decibels per octave, biquads were state-of-the-art, which seemed to be what people find. Around 2006 there was a shift to an apparent innovation known as zero-delay feedback filters. The response of modulating the cutoff of a resonant filter with the new topology behaves like an analog filter, updating with the new cutoff. My rudimentary awareness would describe this as having a better phase response. The 6 decibel low-pass filter form I use is an optimization of a complex form with 2 buffers in an arrangement like 2D rotation, which apparently is sort of the thinking in this innovation. Be careful of habitually cooking your ears with bright digital waveforms. It's nice to be able to see what you're doing, have some visual way to experiment with shaping numbers. One method I like to share, because it took me 16 years to acquire, is the cepstrom. The fast Fourier transform, FFT, is explained in its guide so you can code your own in a dozen lines. The magnitude bins are used to display the spectral contour by log 10. A second Fourier transform is then run on these values to derive the cepstrom. The notation I saw was FFT log 10 FFT. And also bounce